Good morning, everyone, and a very warm welcome to our webinar, Mapping the Heavens, Shaping the Mind. It is an absolute pleasure to introduce our distinguished guest speaker for today's session, Professor Supreet Singh, Assistant Professor in the Department of Physics at the Indian Institute of Technology, Delhi. Professor Singh leads the Quantum Gravitation and Astrophysics Lab at IIT Delhi, where his research spans the frontiers of the theoretical and observational astrophysics from the earliest moments of the universe to the dynamic of the black holes and beyond. Professor Singh completed his PhD in physics from the Inter-University Centre for Astronomy and Astrophysics, Ayuka, Pune, where he was awarded the prestigious V.V. Narlikar Best Thesis Award for his work on quantum fields in curved spacetime. His academic journey also includes advanced studies at the University of Delhi and an outstanding undergraduate performance at Hansraj College. At IIT Delhi, Professor Singh is known for his multidisciplinary approach that bridges astrophysics, physics, mathematics, and cutting edge technology. His work also includes optical astronomy, astroimaging and processing, connecting theoretical foundation with real-world observation and tools used in modern astronomy. In today's talk titled Mapping the Heavens, Shaping the Mind, Professor Singh will take us on an engaging journey through the evolution of astronomy from ancient sky watchers to the modern telescope. He will explore how physics, mathematics, and engineering converge to the illuminating our understanding of the cosmos, and how advancements in technology have shaped not only the way we study the sky, but how these technologies find place in everyday life. The talk will be culminate with exciting insights into India's modern observatories, international collaboration, and recent twin space missions Chandrayaan and Aditya. We are thrilled to have Professor Singh with us today online, but soon we will be hosting his session at Planetarium with students and can discuss things personally. And we look forward for an insightful session. Let's welcome Mr. Supreet Singh. Over to you, sir.
Thank you so much. Thanks for having me here. Uh, really hopeful that with the session today, we'll delve into and ignite many minds, not just in India but all over the world, because we're streaming this online, so it's open to everyone on the planet. So thanks again for having me here. So I'm gonna step a little bit back into my slides and play that thing again. So what gonna be doing is, as I said, we'll be talking on mapping the heavens and shaping the mind. Essentially, I want to inculcate through this particular talk three particular aspects, a trio, which I call them, which are observing, understanding, and predicting, which are not just foundations of astronomy and astrophysics, but all of science, and in fact, I mean, our lives. We This is what we do, and this is what makes us, which quenches our curiosity and takes us forward. So it's a trio, three things put together: observing, understanding, and predicting. I also had a video behind it which was playing. It actually showed comet Neowise, which appeared in 2020. I'll just play that again once more. So you can see there's a whole range of phenomena that is happening. There's stars in the sky. There's the comet. It has two tails which are visible. It has its core, which is again visible, and then there are also clouds in the foreground. And whenever these clouds are moving, it changes intensity. All those things happen. So there's a whole lot of physical phenomena which is happening. Everything is where physics and natural phenomena is involved, and the concepts which go in, when light is traveling to us from these stars on and that comet, and then it is also encountering a lot of medium in between. There's outer space, which has the interstellar medium. Then there is the atmosphere of our planet, which again has many layers. So it has to come through, and a lot of things happen. And whatever happens, these are the phenomena are universal. So this is again another thing which I'll be going through in this particular talk, to sort of tell you how universal the phenomena and the things are. One thing which is applicable in one place would be applicable is also applicable in other places. So it's the universality of things is also important, and as well as this trio of observing, understanding, and predicting. It sort of comes in all together. There are no borders. Borders, I mean, the linings are artificial. But in practice, these things are all together. And I also like to put it as engineering, physics, and mathematics. That is what combines all these things. And particularly in astronomy, it's fairly evident that we need all three things going in hand together to understand and comprehend how our universe works. So let's delve into it. The As I said, it's the in astronomy in particularly, you need all forms of engineering, physics, and mathematics, not just one particular one. There's mechanical engineering, electrical, there's communication. You have to talk with satellites and your telescopes. There's computer science. There's a lot of data which we produce. You have to work with data, algorithms, storing the data. There's material science which is involved. I mean, how your telescopes are made, various things. There's chemical sciences, but then it's all the foundations of physics which is laid on. We have classical mechanics, things moving and all that. And then there's electrodynamics, because everything we understand in terms of light, for instance. There's thermal physics, there's always heat and those things involved. Even in astrophysics, when you're looking at stars, stars are hot, so you need thermal physics and statistical physics there. There's optics, of course. And then there's also quantum physics. People might think, oh wait, how where do we get quantum physics? Is something which is applicable on atomic scales, right? But then in talking about astronomy, these are like astronomical scales. So where's quantum physics there? But if you talk about neutron stars, for instance, there's again, that's the level where quantum physics is important. And in fact, not just neutron stars, inside the sun, the energy is produced via nuclear fusion. So, and that's quantum physics. We would need quantum tunneling in order to produce those reactions. And then you have black holes, of course. So, and early universe, very early universe, how our universe really started. It's all quantum mechanical there. So all forms of physics contributes. And then there's mathematics, because that's the language which we use to do everything. I mean, there's trigonometry, there's calculus, there's complex numbers. You're solving differential equations, and of course you'll be doing statistics, because there's a lot of data which is involved. So math is the language which we use, physics is underlying principles, engineering is techniques that we're using to do our jobs in astronomy. So it comes in together. It's a trio. It's an amalgamation. There's no separateness here, and that's something which is important. So let's delve in. As I said, first thing which I want to really emphasize here, because a lot of us, many of people would be, sometimes they would be at various stages of understanding astronomy. So here's something which comes from Nuffield Physics Teacher's Guide, which was drawn up in 1962 in England, in Britain. The main important thing, they were basically looking at reasons for teaching astronomy, but I want to emphasize one particular thing. When you are learning astronomy, so there's a quote here: please pretend you're back with your earliest ancestors. Why did they worry about the sun, moon, and stars? What did they find out? How did they find out? And how do you and I know? So you see, you have to really get to the bottom of it. It's not like just knowing the facts that the earth is spinning, earth is round, earth is going around the sun, but rather knowing how those facts are indeed valid. You just don't take them at the face value, but rather go out and actually convey. I mean, if the ancestors could do it, you just definitely yourself can. So don't take these facts normally. So if let's say someone asks you about it, hey, prove to me the earth is round, they don't believe it, they say, prove to me. You should be able to do that. Okay, so and there's simple ways to do it. There's all simple experiments, and everyone should be doing that. So it's something very important. Okay. Now, when we are looking out towards the universe, our main window out to the universe is the electromagnetic spectrum. That is light. We see light coming from stars, galaxies, and whatnot. And this light is of multiple different wavelengths. It spans a whole range. It's a continuous wavelength range, and it goes in from radio, microwave, infrared, There's the visible spectrum, which our eyes are sensitive to, is a very small spectrum which is there, 400 nanometers to 700 nanometers. And then you have the UV, there's X-ray and gamma rays. There's a whole spectrum which is of light which is there, and all the celestial sources, they emit light in all these different wavelengths. Okay, so when we are doing astronomy, what we actually essentially are doing is called a multi-wavelength astronomy. Okay, it's not just if you're watching anything with your eyes, it is just only a very small portion of the whole spectrum, which is the visible one. But a lot of phenomena become apparent when you actually expand out. You need other detectors to see in the other wavelengths, radios and all that, and that really tells you, ties up the whole physical phenomena. So if you want to know what is happening in a galaxy, for instance, even a galaxy, for example, here's the whirlpool galaxy, which is shown at different wavelengths. You see, it looks so much different when you view it in radio, in infrared. There's a visible one which you would see if you are looking with your eyes. Then there's the ultraviolet, and then there's X-ray. And all of that, why it looks different is because there's a different physical phenomena that is emitting these different wavelengths. But then these visible physical phenomena are tied with each other. So in order to understand the full galaxy, we need to know it in all the different wavelengths. That is why what we do is multi wavelength astronomy. So here's our own galaxy, the Milky Way, in multiple wavelengths. So you see the radio continuum on top, and there's atomic hydrogen that is also giving you wavelength in 21 centimeter. That is radio. And then there's radio continuum, there's molecular hydrogen, infrared. Infrared is giving you dust grains in the galaxy, these molecules which rotate around, and they're sensitive to that. There's mid infrared, near infrared, and then there's the optical, which you would see in your with your naked eye, and then there's the X-ray, and then gamma ray back. So the Milky Way itself presents in multi-wavelength, and not just the galaxy. There are also individual objects which present themselves in multi-wavelength. So here's, for example, what is called a crab pulsar. So you see, again, once again, there is a multi-wavelength aspect to it. You start with radio, then there is the visible one, there's the UV, and then there is the X-ray. So it's one single object, but there are multiple aspects to it, all linked together. They're coming from different wavelengths, and you connect them up. You actually get to know that this was actually a star which burst itself when it went supernova. It exploded, and the outer, these filaments are the ones which were shed by that explosion. And it, when it has settled down, it has settled down as a neutron star at the center. This is where you see in the X-ray. So you see the whole phenomena what has happened if you view it in a multi-wavelength astronomy. Okay, so now if you want to do multi-wavelength astronomy, the idea is, well, can you do it from the ground? uh, Unfortunately, you cannot do it from the ground because our atmosphere presents a hindrance. Okay, because our atmosphere absorbs certain wavelength, like for example infrared and also UV, which is good for us, because if UV light would be coming down to the ground, it would be harmful to us. So it is absorbing that. So since you are able to see the stars by your eyes, that tells you our atmosphere is transparent, almost transparent at visible in the visible region of the spectrum, and that is why we are able to see the stars. So that tells you the inference, right? How do you draw the inference that the atmosphere is transparent? By, if we can see the stars, that tells us indeed where the light is coming through it almost unobstructed. There are of course some distortions due to the atmosphere, but it is almost unobstructed. But if your eyes would be viewing in infrared, you will not be able to see the stars, because of that, those are blocked by they're absorbed by the atmosphere. And same thing happens for gamma rays, X-rays, and UV. But radio waves, again, they are transparent, so you are able to for a greater degree, so you are able to do radio astronomy from the ground. We can keep the radio telescopes on the ground and observe the objects from the ground. But for the other things, it's therefore required to put our observatories, our telescopes, out in space. So therefore you will find the gamma ray, X-ray observatories in space. Like, for example, there's the Chandra X-ray Observatory, which is there in space. The infrared observatory called Spitzer is also there in space. JWST is an infrared telescope. It is also put up in space, and so on and so forth. Okay, so that is the idea for multi-wavelength astronomy. Why you really need some observatories to be put up in space, and some things which you can do it from the ground. But as I said, it's a multi wavelength astronomy. But now we have also embarked into understanding the universe through another window which has opened up, which is the window of the gravitational waves. So we have these telescopes called LIGO, which are detectors which detect not light but gravitational waves. And there are objects in the universe which also send out gravitational waves. In fact, all objects do, because they have mass and energy. And whenever something has mass energy, they lead to gravity. So they're sending off gravitational waves. So if we have telescopes which can detect them, we can view these objects also through gravitational waves. So that is why it has now multi wavelength astronomy. Now, presently, in the exciting era, it has become multi messenger astronomy. So you just don't have a messenger which was light earlier, but you also have added another messenger, which is the gravitational wave. And then we can also do it with neutrinos. There would be another messenger to add in the near future. Okay, so now let's go to the past. How in the ancient times it all started. Well, astronomy has been for a long. It's fascinated. The sky has fascinated humans for a long time, and this one is a shield, for example, a bronze shield from 1600 BC. It shows various, you know, I mean, you can make out that this is showing the stars and the moon. So there's people were really fascinated by it. They wanted to keep records of the whole thing, and so they started to view the motion of the stars in the sky. Of course, it's due to the Earth rotating around its axis. So the coming of seasons and everything, and that really put push forward. Pushed it to try to understand how this whole thing is working. Okay, and also of course use it, because the knowledge of seasons and how time is varying was important for various purposes, like agriculture and various things. So this thing has been going on for a long time. As I said, this is there are another other examples of it. Like there is the Babylonian observation of the Halley's comet in 164 BC. Then there is the Greek Antikythera mechanism, which is over here. And then we also have the Jantar Mantar in India. Okay, so that those are again observatories which people built to study astronomical phenomena. Now, the list which I have shown here is not. I mean, there are a lot many things there, so I cannot put everything. So I just tried to show some of the glimpses here. It's inexhaustive list which is there. So people really wanted to understand how things are moving. Okay, so I'm going to go back and forth between the astronomical aspects or the physical aspects, and also the technologies and all those things which came in. Now, when you have these technologies of observing things, you want to really point out how, I mean, you want to find how things are moving. You want to know where things are in the sky. Let's say you have a star in the sky. You want to give it a position, and let's say you want to tell your friend, hey, I see something there. You also look up at the sky in this particular direction at this particular position. So you need to tell coordinates to sort of relay coordinates where to look. And that sort of started the field of what is called positional astronomy, which gave positions of objects in the sky. And it's a simple deal. I mean, just to sort of show you how it's done, you stand up on the ground and you find your north, wherever north is, and that is your 0 degree to set up in what is called azimuth, because you're standing on the ground. This red circle is sort of your ground or your horizon. So once you have north, automatically you have the east, west, and the south. Okay, this is dictated by 90, moving 90 degrees around the circle. So you're standing there, and now when you're viewing the sky is just I mean right on top of you. So you have there's the position which is directly above your head, which is called the zenith. So you make an imaginary line which is called the meridian. Okay, the sky is like a hemisphere above you. So this meridian is a line which goes from north all the way to south through the topmost point, which is the zenith. And this meridian automatically is dividing this hemisphere into two halves. So there is the eastern part and there is the western part of the hemisphere. So now if you have a star in the sky on this particular hemisphere, you can give it a position by simply declaring how high it is. That is telling you what is the altitude of the star or the elevation, and then how far did you have to move away from your north position. Okay, because it is spread around, so that particular coordinate is called azimuth. So you have two coordinates, altitude and azimuth, which specify for you what is the position of the star in the sky. So if your friend is also nearby in the same region or something, I mean, not too far away, the same coordinates will work. But if you are at different places, let's say your friend is in, you are in Delhi, your friend is in Mumbai, and you give these positions, they will not work because the earth is round. You have to set up the coordinate system which you have set up would be different from the coordinate system of your friend. Your skies will be slightly different because you are at two different places on the earth. But we know how to, make sense of those as well. Nevertheless, this is the case where you are standing, and then there is also the north celestial pole of the earth, where there's a well-known star which is very near this particular place. It's called Polaris, because the earth is spinning around its axis. So since it is spinning around the axis, this axis is what is pointing towards the north celestial pole, and therefore you can draw uh, another curve, another line, which is called the celestial equator. This is just 90 degrees from the pole. Okay, just like you have the red line is 90 degrees from the meridian, the celestial equator is 90 degrees from the pole. And now you know that the stars rise and they set because the earth is spinning. So whenever there would be the spin of the earth, they will rise from the east, and then set in the west. So they'll just go around, just like, for example, if they are right at the equator, they would rise like that and set in the west. Okay, so just because the earth is spinning around its axis, and it's easy enough to find coordinates of any object in the sky. You can do it yourself. You can make something like this. It is called a theodolite. Okay, so this is a simple uh, object. I mean, it's a setup apparatus where again you have a straw here, which through which you can look at the object in the sky, and you have two protractors. So there's a protractor built in underneath the straw, and then there is one which is on the base. So now just like in what I mentioned in the previous slide, um, the the bottom one is telling you the azimuth, how far you have to move away from the north as you view the object in the sky. And the top one gives you the altitude, how high it is in the sky. So the two coordinates, once you find them out, you can relay it to anyone in the vicinity of your region, in the nearby region, and they can also look at the same point in the sky and see the same object to which you are looking at. See? So it's a simple enough apparatus anyone can make. If you do not have this apparatus, there's a simple another way to work it out is by using your own hands. So normally, generally, our hands are such that it's the angles, because again we are finding angles of in the sky, right? How high it is. That is why we had those protractors there. So something is directly above your head is 90 degrees high in altitude. Something which is right at the horizon is at 0 degrees. So you can find these angles by also using your hands. So here, for example, let's say the tip of the thumb and the index finger, it is the separation is around 25 degrees. Okay, so you could use this. So of course it change. I mean, not everyone has the same set of, I mean, similar hands. So but almost this would be around 25 degrees. Or maybe you could view this particular object, which is the constellation of Big Dipper, and we know that the separation here between the two stars on the left and the right is 25 degrees. You can find out how much is this angular separation between your index finger and the thumb. Okay, so and calibrate it accordingly. So here's this is another way to find altitude and azimuth even if you do not have any apparatus on hand. So this is what people have been doing in ancient astronomy. They built various these things and tried to locate positions of objects in the sky, and also how they changed uh, during the day, during months, and in a year. How things were moving in the sky, and that led to since they were doing all the finding positions and everything, is actually led to the development of mathematics, and particularly trigonometry and spherical trigonometry. So this is how sort of math, it's these things, as I said, engineering, physics, and maths, they don't just, they feed back into each other. You use some physics, you use some math to do some physics, and then some physics will also tell you about some math. You do some engineering to do it. So it also sort of mixes up with each other and feeds back into it. So this is something which was important. As I said, it developed mathematics, how to sort of understand the movement of object position and movement of objects in the sky. And people also found the sizes of astronomical bodies, and starting with size of our own planet, the earth. Now if earth is a large planet, you don't really go around measuring with a measuring tape what is the size of the earth. So you have to be really ingenious to find ways to measure the circumference of the earth or the radius of the earth. And this is where this ingenuity comes in. And this was done in ancient Greeks time, right? So this Eratosthenes did this experiment. He found that on a particular day, at two places, there were two towers. These two places are separated by 780 kilometers, and he saw that on that particular day, at play the two places, there would be, at one place there will not be any shadow of this tower, and at the same time there would be a shadow cast by the tower at a different place 780 kilometers away, and the extent of the shadow was around 7 degrees. So by knowing the distance between the two places and measuring the extent of the shadow, which here is around 7 degrees, he was able to find the circumference of the earth around 40,000 kilometers. And hence, assuming that the earth is perfectly round and the circumference would be a circle, he found that the radius would be around 6,300 kilometers. It's a fairly a good estimate of what the radius of the earth is. Of course, assumptions go in, but this is what tells you how to estimate things. Because we know that the earth is, of course, not perfectly round because it's spinning, and once the objects are spinning, they tend to get flattened at the poles, at the axis, and they get to bulge out at the equator. So it's not really perfectly spherical, but nevertheless, with certain assumptions, you tend to find these numbers easily. So this was done at the Greeks' time. Certainly something which you can do also today, right? And there are different ways to measure the radius of the earth. So this is one of my points in this talk, is to really send this message out, to have the audience, go forward and do these experiments, which are very simple to do, and perform them, and then really understand, not just take the facts at the face value, but really understand these things. So here's a simple one. uh, it's a paper on using a video camera to measure the radius of the earth. Essentially, what is happening is you find a tall building, and then you uh, take a video camera, essentially an iPhone. They just took a smartphone there, and they found how much time it took for the shadow to recede during the sunset as the sun is setting. I mean, the earth is rotating around, so therefore the building would be lit, but as it rotates, the shadow will go up, and it rise up from the ground to the top of the building. So you find how much time it takes, and again you can use that to find the radius of the earth. So in this one, they again found the radius, which was around 6394.3 kilometers, within 1.8% accuracy. Again, a very simple experiment to do. All you need is a smartphone and a tall building near your place. So this is something which you can do. There are other places, ways to also find the earth's size. You can, there's another one. This one is doubling your sunset. Okay. So to give you an example how I use this particular method, I was flying out of Delhi, and right when my flight was about to take off near the runway, I actually saw the sun setting. So it was around 5:30 p.m., and so it was right near the horizon, and so I saw it set. I actually took a picture just to note down what was the time, and then the plane took off. When it took off, it got to the height of 33,000 feet, and I again saw the sun set after 16 minutes. So that there was a time gap of 16 minutes because you are at a very high. I was at 33,000 feet, so I could see the sun set again. So you are doubling your sunsets, and by using how much time it elapsed between that, again you can find the radius of the Earth. Okay? So once you found the radius of the Earth, it in astronomy what happens is that finding and estimating distances is goes in steps. That is, it's called a ladder. If you want to find the distance to the moon, for example, again, as I said, these are astronomical distances. You cannot take a tape measure and really measure it, across. So what you do is you find ingenious ways, and the ways of course require, for example, this one, in order to find distance to the moon, requires you to know what is the size of the earth. Okay. So if you know the size of the earth, you can find the distance to the moon. Again, you do this particular experiment. It's a simple one. You can also determine the eccentricity of the moon's orbit. And sometimes people say, hey, well, we need a telescope to do all these things. No, actually, you do not. Here's an example where the eccentricity of moon's orbit is determined without a telescope. And let me show you the what they used. They basically used a piece of cardboard with a small hole in it and a yardstick. This is a simple device, and they used this particular device, got the data, and hence determined what is the eccentricity of the orbit of the moon. It's not perfectly circular. It's almost circular, so you can find that small deviation from the circular orbit which is there. Okay, so all these simple experiments are something which can be done by anyone. You can measure the orbital period of the moon using a digital camera. Again, another one which is there. Um, Once you have gone to the moon, the next thing is, of course, going to the sun. Okay. And just like as I said before, so measuring, this is what we know call the astronomical unit. It's the distance between the earth and the sun. So this is the third rung of the what is called cosmological distance ladder, after the radius of the earth and the distance to the moon. So you found the radius of the earth, that is useful to find distance to the moon. And when you want to find the distance to the sun, you require the distance to the moon, and hence you also require the distance to the radius of the earth. So it goes in step. You go up this ladder, and once you know the distance to the sun, you can find distance to the stars. Okay, so this goes up like that. So this is again another one. As I said, it uses um again, this was done by Greeks, Aristarchus, and then something which can be done again. There are various ways. So in science, another important aspect is that if you do something in one way, you need to find and also do it in another way that would be independent of the previous one. Because if you have two distinct different measurements of the same thing by different means and they agree, then it really gives you a confirmation of the fact. So in science, you just don't do one thing, but you also confirm it by alternate independent means. So there are different methods to find the determine the, for example here, determine the distance between the earth and the sun. uh, there's this one, this is another way, by using Venus. So whenever Venus comes in between earth and the sun, which we call as the transit of Venus. So there are ways to find the distance to the sun using this as well, and people have done it. So moving on, as I said, once you know the distance to the sun, this is where you can use it to climb further up your ladder, get distance to the stars. And this is where, again, something which comes in. The ingenuity here is that you look at the star as the earth goes around the sun. So it takes a whole year to go around the sun. So you can observe this particular star at two different points. When the earth is over here and it is viewing, so if this is the orbit, is 90 degrees to the orbit, or you can view the star when it is at this particular point. So you can therefore have two different stars, how they move around. And so the earth would be here or the earth would be here, and you are viewing the star. It will What will happen is, you will see that as if the background of the star changes when you are viewing the star from two different points on the orbit. Okay, I will just show you the animation here. So let me just put in before that, just to mention that this method was first used by Frederick Bessel. And when you normally come across Bessel in your in when you're learning physics or something, we usually come across Bessel. There are these functions in mathematics. They're called Bessel functions. These are actually shown here on the stamp as well. So he did a lot of mathematics. But here's a stamp which was released in Germany, and commemorating him. And you see what is written here. It says Bessel, astronomer and mathematician. So he was an astronomer first and then the mathematician. Okay, and he used this method of trigonometric parallax to find distance to the star named 61 Cygni. And what did is a similar thing. He tried to observe this particular star at two different points on the Earth's orbit. Now, let me show you what happens when you observe these things from two different points. So, here's the animation. So, you see, when you are seeing it from two different places, the star appears to shift its position with respect to the background. Okay, so this is, but it's not really actually moving. What is happening is you are viewing it from two different places. Okay, so using this particular shift, you can actually find what is the angle of the shift. And but this angle is something which you can find using the shift, but you want to really find the distance to the star. The distance to the star is related to this angle and the distance between the earth and the sun. That is why I mentioned that this thing is required in order to move forward. So if you know the distance between the earth and the sun, you observe this particular shift which gives you this angle, you can find the distance to the star. Well, that is how you go beyond the sun. Okay, and how all this finding positions of objects in the sky, distances, how they have shaped our understanding of the universe. Well, here's an example. um, Earlier people used to think that earth is at the center and everything else is going around it. Okay, so those were called geocentric models. And well, it was not it was not unreasonable, because after all, you are here on the earth and you do see everything going around it. Okay, so, and someone could, again, there's an example where someone would say, hey, I see everything going around me. The sun is going around the earth, the stars are going around the earth. How can you say the earth is not at the center? Okay, and so this is what people actually did. They saw the motion of Mars in the sky, and again, noting down positions, right? So you're noting down positions of objects in the sky. So they saw that it is moving in the sky on different days. So this image, for example, is taken on successive days. It seems as if it retraces its path in the sky. It's going backwards in the sky and then moving forward again. Okay. Now, if things are going around the earth, certainly this thing cannot happen, because if they're going around the earth, it would just be a straight path. They would not retrace its path. But it seems to be happening. And the only way this can happen is earth is not at the center, but rather it's the sun which is at the center, and earth's orbit is the orbit, the before Mars, so the inner orbit than Mars. Mars has an outer or the orbit compared to Earth. And then what happens, as the Earth goes around the sun, Mars is also going around the sun. And so it can happen that when this is going on, because the Earth is in the inner orbit, it can overtake Mars. When it overtakes Mars, and when we are looking at Mars in the sky, with respect to the background, it will show this shift as if it is going backward. So therefore, these understanding, knowing the positions of objects in the sky, they actually told us more about physics, about understanding our own solar system. So this is how the it feeds back in. And there are various examples where theories led to discoveries, and where observations also guided theories. Like, for example, Alexis Bouvard published her tables of Uranus, and they found discrepancies. And then Leverrier was an astronomer. He said, hey, this problem in Uranus could be due to something happening in the there could be a planet there which could be causing it. And he worked out math and found where the planet would be, and told astronomers, look in the sky at this particular position. And they looked there and they found Neptune. So Neptune was found by pen and paper. That is, people knew about Uranus, and there was a problem in the Uranus, the positions of Uranus. So this guy assumed that there was a planet outside Uranus causing this. And due to a disturbance of that planet, due to the gravity of Neptune, this was happening. And he found where Neptune was, told them where to look, and they found Neptune. And then there were also, as I said, uh, where observations guided theories. Like, for example, there was all this problem of the orbit was also there with Mercury. And this guy said, well, there could be another planet near Mercury causing that disturbance. But people looked, they found nothing. So in this particular case, it is not the planet which was causing the problem in the disturbance in the orbit of Mercury, but rather a change in theory was required. And this is where Newtonian gravity was replaced by, or it was superseded by, a more general theory, the general theory of relativity given by Einstein. He came up with different theories, and he came up with general relativity. He stopped when he got the right number. He kept computing this number of 43 arc second shift in the orbit per century, shift in the orbit of perihelion of Mercury. And general relativity was developed to sort of explain this. It was the new theory of gravity. But then, as I said, you need to confirm your theories independently. So Einstein also predicted that light would be bent uh, by any star or any massive object due to gravity. And in particular, if you have a star which is, let's say, very close to the sun, and the light is coming from the sun, it would be bent by the gravity of the sun. And so you will see that the position of the object will shift, position of the star will shift because the light has bent around it. And this thing could be observed. Of course, you if you want to see, look at a star near the sun, you have to shield the sun because the sun's light is glaring. So this can be done during eclipses. And of course, during the 1919 eclipse, Eddington led an expedition. This is the kind of telescopes they used, the engineering which went into it, and they indeed saw that the shift was there, predicted by Einstein, and that confirmed general theory of relativity. Okay, as we know, the new theory of gravity. And now this bending of light has been seen in various other cases, not just by the sun, but also by galaxies and galaxy clusters. So if you have a huge cluster of galaxy that, and you have some particular object behind it, you again see that the light gets bent, and you see images of the objects in the sky. Okay. And the same thing had also been seen if you have a black hole that also bends light around itself due to its strong gravity. And you see that the image around the black hole turns out to be something like this. Is the simulation which was done. Uh, and we actually observed this simulation with the telescope. I mean, we observed galaxy black hole with the at the center of M87 galaxy with our telescopes, and we actually found it looks like that. Okay, so this is happening due to extreme bending of light, and there is a black hole at the center of uh, this galaxy. It's called the M87 galaxy. This black hole is 6.5 billion times the mass of the sun. It is accreting matter, that is, matter is falling into it, and the amount of matter which it is falling into is 90 times the mass of the earth per day. Yes. And its size, the angular diameter, is 42 micro arc second. So just to put it in the perspective, if I put the sun in the center, and then this would be the orbit of the Pluto, and this is the object, the Voyager 1 spacecraft, how far it has reached. So this is the size of this black hole at the center of the galaxy M87. So we have also mapped our own galaxy, the Milky Way, how it looks like, even while we are within the galaxy. So it's something which is amazing. You're trying to map how your home looks like from within. Okay, so you cannot get out of the galaxy to see it. So how do you do that? You do it by observing objects in the sky and mapping them where they are. There are various objects here. Like for example, I just want to give you examples. The Rosette Nebula, molecular gas clouds there. There's the Orion Nebula, which many people would know about, is very easily visible in the sky. But then, in order to map this galaxy, we use a very ingenious way. All over the galaxy, there are these stars which are called pulsars. There are neutron stars. They are sending beams of light around. So they are like lighthouses. Just like a lighthouse sends a beam of light, these pulsars are also rapidly spinning neutron stars, and they are sending these beams of light around it. So we look at these beams of light as they come from these pulsars all over the Milky Way. And by looking at when light is coming through towards us from these pulsars, there are tons of things, as I said, in between us and the star. So the example which I showed earlier, that Crab Nebula, it is also a pulsar. So there is stuff between us, and most of that stuff is electrons and various things. It's like plasma which is there, and when light comes through to us, it gets disturbed. So the it disturbs the electrons on the way, and it spreads. By finding how much is the spread, we can find how much is what is the density of electrons which cause this particular spread, and that allows us to make the model of our own galaxy, which looks like a spiral. So it's a spiral galaxy. So, and the phenomena, as I said, there's very universal in nature. After all, what is happening is light is getting scattered around, because light is coming to us, whatever stuff in between, it scatters things around. And this is the same thing which also why is the reason why we see a blue sky during the daytime, and why you see a red sunset. Because what happens is light is coming to us, our atmosphere scatters light. So during the amount of scattering depends on the wavelength. The longer wavelengths, the red light gets scattered less compared to the bluer one. Blue wavelengths scatter more. So during the daytime, the sun is higher up in the sky. So you therefore the blue light comes to us directly. But when the sun is setting, it is close to the horizon. So therefore, the red wavelengths, the longer wavelengths pass through without too much scattering. So we see a red sunset compared to blue sky during the daytime. And this is again something happens when you are also watching stars. So if you take a star, for example, and light is coming from the star, if there is something in between, just like our atmosphere is in between the sun and the ground. So if there is a dust cloud, there would be, if you are at position A, you would see light which would be red light, mostly longer wavelength passing through. But if you are at position B, you would see a reflection which would be a bluer reflection. And it is exactly what we see here. For example, here's this is a bunch of stars which is called Pleiades, and here you are at position B. That is, light, the blue light is getting reflected towards you. And here is another object, which is the Horsehead Nebula in the sky. And here you is at position A with respect to the star. So the blue light is going somewhere else. It is the red and the longer wavelengths which are passing through it. So you're seeing a brownish object here rather than a bluer one, which was there in the last previous one. So you see what is happening, what gives you a blue sky and a red sunset are the similar concepts which are also happening here in astronomy. So the concepts are universal in nature. So coming to the technological side of things, in order to do astronomy, a lot of technology had to develop, and particularly what got developed are called the detectors, because we are looking at light. So we want to detect light. The CCD cameras were actually developed in astronomy to record light using the telescopes. And now these CCD cameras, they have made it into the cameras in your hand, the smartphones. These were developed for astronomy. And then there is also this computational imaging. Nowadays, when you take a picture in your smartphone, it is not just taking one single picture. It's actually taking many pictures in a very small time. In, let's say, in a 1 second, it will take hundreds of pictures and combine them. And what happens then is that if you are taking images at night, you know that in dark situations you do not have too much light, so your signal is very weak and there is lots of noise. So in order to reduce noise, what this is something which we have been doing in astronomy all the way, because we observe these objects which are so far away, these stars, there's a lot of noise but very less signal. So what we have been doing is we take many images and then we combine them. So this is what is called computational imaging. And now this computational imaging is also done by smartphones in your hand when you take images during the night. So another important technology that trickled down from astronomy to our real lives is of Wi-Fi. The wireless these networks were actually developed by an Australian astronomer, John O'Sullivan, who was working in radio astronomy. So he wanted a way to transfer data from his computer wirelessly, and that's how wireless networks developed, and that is what developed into modern day Wi-Fi technologies. Then there is, you also used your nowadays we have these we can open doors by using cards. And if you go to a hotel particularly, you open these doors, there are these special locks, you just present a card, it opens up. The terahertz technology which is being used there in securities and all that, it actually emerged from sub-millimeter astronomy. We also have the GPS systems. They actually were something which utilized general relativity. And so there's a whole lot of technology which has trickled down by from astronomy. When we are doing science, it comes down to the society. Here is another example. What it shows you is actually a solar eclipse here. So you cannot see the sun because there's the moon which is hiding the sun. But outside, the just around it, there is this corona, that is the outer atmosphere of the sun, and that gets visible during the solar eclipse. Now, if you want to see that light which is coming from the solar corona, and you expand it out using a prism or a diffraction grating, that is, you want to see what are the wavelengths which are there inside it, you see a whole spectrum of light which is there, from all the way from the visible light, they're going from violet to red. So there are distinct lines which are there, and you know that each line is tells you what elements are there in the corona. And in particular, there is a line which is the helium line, which was s- visible in the corona, is at 587 nanometer. Helium was not known as an element on Earth. It was actually first discovered. The evidence was observed on uh, on August 18 as a bright yellow line with a wavelength 587 nanometers in the spectrum of the chromosphere of the sun. It was detected by a French astronomer during a total solar eclipse in India in 1868. So this is how, that is why it was named helium, because helium means in the sky. So helium was observed in the sky, and then subsequently it was found on the also on Earth. So this is how it's the astronomy has sort of contributed not just to the technology in our daily lives, but also to our understanding of the universe. We now understand our universe all the way to the past, how it came about, and this is something amazing that we are able to understand universe all the way back to 13.7 billion years, and all of this has come around by amalgamation of technology, physics, and of course mathematics. So here's another example which I want to show to tell you how the universality of concepts again comes in. Our universe is almost what is called homogeneous. That is, if you look around, if you are looking at it from a very large patch, that is, if you take a box size of a very large box size which we call the size of 100 megaparsec or so, and if you look around, it looks the same. And if you change places, again you look around, it almost looks the same. Okay, but these galaxies which are formed, they must have formed due to gravity by virtue of things coming together. Okay, and the way they are formed is very similar to what you, if you look at a particular, let's say you go to a swimming pool or something, and which is a shallow body of water, you would have noticed on a shallow body of water that there are these filaments of light which can be seen. Okay, so, and how are these filaments of light formed? Essentially what is happening is that the water on surface, it's not planar, but it's moving, okay, due to wind and everything. And so some, at some places there is more water compared to other places where there is less water. And when light is falling in, it converges or diverges. Whenever the water is more somewhere, it is behaves like a convex lens. It converges light, and that leads to these bright areas. And wherever this is, there is less water, it behaves like a concave lens. It diverges light, and that gives you a dark area. So these, therefore these filaments form, and in a way our galaxies also formed like filaments in the sky. Okay, so the same concept uh, which is actually forming galaxies is also there in shallow bodies of water and swimming pools. The same thing, the same phenomena acting in two different places. So, as I said, it is an amalgamation of basic science and engineering. You need science and technology to do astronomy. India is already contributing a great deal in astronomy and astrophysics via indigenous as well as multinational projects. We have several telescopes. I'll be so we also have this international liquid mirror telescope, which is installed at Aries in Devasthal campus near Nainital. It's a collaboration between India, Belgium, and Canada. This telescope is one of its kind because the mirror here is actually liquid mercury, which is kept in a rotating platform. So that makes it into a particular shape, the parabolic shape, and makes a mirror that is required for a telescope. So that's why it's the International Liquid Mirror Telescope. India is also part of the 30-meter telescope, which will come up. It's a wide, big consortium. Then India is also part of the Square Kilometer Array, the Radio Astronomy Telescope. These are the next generation telescopes. ILMT is already working. We have the Asia's largest optical telescope, the 3.6-meter dot installed at Devasthal, again near Nainital. Uh, we have the giant meter wave radio telescope, GMRT, near Pune. We have the Udaipur Solar Observatory, which is involved in solar observations. Um, then we have the Himalayan Chandra telescope, which is installed at Leh, near it's in Ladakh at Hanle. And then there are various other observatories. Again, the list is there's a lot more in the list. Uh, and now we have also have observatories in space. We have gone to the moon, and we have also gone. We are looking at the sun from space through our missions, Chandrayaan and Aditya L1. So Chandrayaan mission had there are three missions. The first flight happened on 22nd October 2008. We had two successful orbiters. Then there was also a soft landing and rover deployment on 23rd of August 2023, and several objectives were completed during all these three runs. Here's, for example, an animation of how Chandrayaan was sent to the moon. So it was there are these series of maneuvers which what are called orbital raising maneuvers, which allow raising the orbit and using gravity to actually propel the spacecraft in space. So this is what they did, and injected the Chandrayaan into moon's orbit. And it is actually tremendous success of Newtonian mechanics. So something which we always sometimes say, hey, when Einstein came in, the special relativity was developed, and then general relativity got developed. So there are these new theories. What became of Newtonian mechanics? Is it still applicable? Yes, it's this is all theories when they are developed, they have a domain of applicability. And Newtonian mechanics, for example, remains valid in these environments. So it's a spectacular success of Newtonian mechanics. um, so Chandrayaan confirmed water on the moon. It mapped the far side of the moon. Then there was also chemical mapping of the entire lunar surface. It explored South Pole. Um, they, it also checked the surface temperature variation, detected sulfur, and also took plasma and seismic measurements on the moon. Uh, Now, once we have gone to the moon, the next step, as I said, is going to study the sun, our personal star. And this is what we did with Aditya L1. But before getting to that, um, of course, people would normally, if you look at the sun, it looks quite boring. I mean, it's just giving off light, right? But here's a visual of the sun in a different wavelength. And you see there's a whole lot of activity which is going on the sun. There's during the years. So there are times, there are years when there's not much activity, and then there are years when a lot of activity takes place. So the sun is going through various, it goes through cycles of activity. It's called the 11-year cycle. And to understand what is happening, I mean, understanding stars is way more difficult, but then we have a star very nearby which we can see very clearly, magnified way. And understanding how stars work is requires understanding how the sun is working. So this is happening, this all this activity is happening because of magnetic fields on the sun. The sun has very violent magnetic fields on its surface, and that is what is causing this activity. And why it is important is because the sun is also spewing away particles, highly energetic particles, which is called solar wind. And this is all the time going directed away from the sun. These particles are moving at very high velocities, and then of course these also come up towards the earth, and they affect whatever is happening on the earth. Most of the time we are shielded because the earth has its own magnetic field as well, so it deflects away these particles. And when it does so, this is what gives you these phenomena of auroras or the northern lights. which are seen at the north and the south poles. Uh, but often, sometimes the solar wind can be very strong and powerful, and therefore it can cause problems in the communication systems on the earth, and various things like even flights can be affected. Recently, Airbus announced there were some issues with certain uh, Airbus 320s, I believe, due to the solar disturbances. So they had to take care of that. So in order to understand all these things, we really need to know how the sun is working, and particularly also the outer atmosphere of the sun. So we study the outer atmosphere of the sun, the solar corona, during the solar eclipses, because that is when it becomes visible to us, when the photosphere of the sun is hidden behind the moon. And then, as I said, the sun also is emitting different wavelengths. So it has to be studied in multiple different wavelengths, not just in one single wavelength. And this is, for example, how it looks like in different wavelengths. And in order to do that, we can study only the visible and the radio waves from the earth, but rest of them we need to go out into space. Suppose you want to study the sun in UV, you have to do it from space, and that is where the Aditya L1 mission also came in. It has several payloads on it, several different telescopes. Again, there is this animation showing um, how it was injected out, sent out to this particular point called the L1 point. It is a point between the sun and the earth, and that is where it goes around this point the halo orbit, and it stays there and watches the sun all the time, constantly, and sends back data back to us, to earth. And so it's studying the dynamics of the sun's chromosphere and corona. It's also studying the coronal heating problem and the mass ejection. It's studying the physical particle environment at L1, what the solar wind is. It is also studying various processes below the solar corona, and also looking at the solar wind and the space weather. So there are how it does that. It has different payloads. There is the visible emission line coronagraph, that is looking in visible light. Then, as I said, you want to do it in UV. So there is the Solar Ultraviolet Imaging Telescope called SUIT, that is looking at the sun in ultraviolet. There is the X-ray spectrometer. There is the orbiting, again, X-ray spectrometer, which is there. There are two of them, soft and hard X-rays in two different regions. And then there are different other payloads for studying the solar wind and also the magnetic field at that particular location, L1. So all these things are there. And I just want to end up by mentioning that if you are doing astronomy, there are various career options which are available, because astronomy, as we have seen through the talk, it encompasses all kinds of science and all kinds of engineering. So you just don't have physics, but you have physics, chemistry, mathematics, biology, even like people are doing astrobiology, how the various origins of life came up in the universe. But then also all forms of engineering. You have the computer science, mechanical, electronics, electrical, and all of these things are there. So, and various career options which one can take up. There are various arenas to work in astronomy, in theoretical and observational astronomy, based on what you want to do. There are different career positions, and then there's, of course, everyone should also involve, anyone who is astronomy should also involve themselves in outreach activities. That is, it's whatever knowledge you have gained, you spread it out as well. So all these things are there. And so with this, I would like to end by saying that it's the dawn of new science and technology in India at the moment, and exciting times for astronomy and astrophysics.
What a wonderful session it was, sir. So we have few questions actually.
Sure.
Uh,
um, I
okay. So
can,
the
yeah.
first question by Anmol Gandhi. Why
Mhm.
did Bessel choose 61 Cygni in particular for the first successful parallax measurement?
Why did he chose okay, yeah. So actually there were different stars which were chosen. The it is actually not easy to find these parallax measurements. So it involves not just find. So if I just go back to the slide there, um, so usually you, yeah. So usually you would think that you would just you want to find how what is the angle of deviation. This angle of deviation is very small. It is not easy to measure this angle, especially when this was done in 1838. This thing, what you see here, is with modern satellite, Hipparcos. But going back here, so this measuring the difference is not easy. What actually is measured is the next difference of the difference. This is the second order there, and that is what was done. So there were different objects he was able to find successfully for 61 Cygni.
Okay, next question is, without stellar parallax, how would astronomers have proved that stars are extremely far away? By Pritesh Saluja.
Oh, okay. uh, yeah, without finding actual distances. Well, the first thing is, of course, the way you would argue is, if these stars are similar to the sun. Okay, because the sun is also a star. These are these uh, giving off light, and these stars do not appear to be as bright as the sun. Okay, so we know that if you keep a same brightness object of the same brightness, let's say you have a truck and it keeps its headlight, and I keep this truck at different distances, just because the truck is near me, it will appear way more brighter than when it is kept at a very far away distance, because light spreads around, and it spreads as the inverse of the square of the distance between the source and the observer. So because if these stars are like our sun, if they would be very close to us, they would have appeared way more brighter, just like the sun. So our night sky would be equally bright. So that sort of tells us that, yeah, these are way far off.
Okay. Next question is, without satellites like Hipparcos or Gyagi, would precise parallax measurements still be possible today? By Ritu.
Without these satellites, no, because they're required, um, for a very fact that getting precise parallax measurements requires you to find. So once again, if I want to play this thing, you want to find how these objects are moving in the sky, that their positions are changing. Okay, now our atmosphere also causes a hindrance, because our atmosphere is turbulent. So this is why when you look at the stars in the sky, they you see the scintillation, which we call, so I mean, in the colloquial language, called twinkling of the stars. So that is happening because of this precise reason, that light is not directly coming to us, but it also gets scattered by the turbulent atmosphere. So the atmosphere also causes these shifts. So we want to determine if you want to determine the shift, the parallax precisely, you want to get it done without the atmosphere, and that is why these satellites were put out in space to do these observations. That is, we do not want any atmosphere to hamper us. We want to do it without the atmospheric effects, put it out in space, and then get these precise measurements.
Okay. Next question is, did mapping the heavens push astronomy to become more mathematical and abstract? By Rishabh Jain.
Not really, because astronomy has not become mathematical or abstract, because there's always a physical process behind it. You see, um, if I go back to the, so here's, for example, getting we got to know about the solar system, but then as we have gone back, known more about our universe, of course the processes are complicated, but then the physical reasoning behind them is way simple. So for example, let me just see where, if I have it here. um, Okay, just to no. So okay, uh, again, just to sort of again answer the question. So even though the math is always there behind it, because mathematics is the language which we use, because any theory does not make any sense unless we can make predictions. Okay, and if you want to make predictions, you need to bring in math. That is where the math helps. Okay, so it's just not words. You have to put things in equations and everything, but the physical picture behind all these things is very important. Well, what this is what I mentioned before also. Here, when the galaxies are being formed, it is the same thing which is giving you these not these filaments of light in if you look at a pond or something, or a shallow pond or a swimming pool, you see these patterns of light, and the same patterns of light are also there. I mean, not light, the same phenomena is what is there which formed our galaxies. The galaxies also exist in these filamentary structures, and let me see if I can pull that up just to sort of uh, uh, if I just Google up filaments of galaxies, yeah, so they, yeah, so here it is. So this is how these galactic filaments look like, and the phenomena of physics is the same what is happening here compared to what is the light patterns in uh, swimming pool. Let's say. See if they come up. You see how similar those things are. And here this is happening with light, there it is happening with galaxies. So the physics is the same. It's important not to get lost in the math, because math is something in the background. Just like we are talking with each other, we are interacting, we're using English as a medium, as a language to interact, but we're not getting lost in the language. Of course, language has its own nuances and things. People like to study math as well, and that is very important on its own. But here, when you're studying physics, is the physical insight which sort of matters. So that's something which is how that works.
I hope that answers the question. So, okay, Sandeep Kumar is saying it makes me sad that in this vast population of India, only 13 people are watching. So, sir, the session was really good, but
Mhm.
we can't connect with lot of people. But this is live, so anyone can watch it later on.
Well, I would say share it with your friends and family and everyone around. This video will be there on YouTube forever, so it's not going to go away. Of course, less number of people watched it online, but then this is where the outreach. Every each one of you has a responsibility to do science outreach and send it out wide and you know wherever, and it'll reach.
Anmol Gandhi is saying, thank you so much, sir. Wonderful session it was.
Really welcome. Yeah.
And Prerna says, what an amazing talk, Professor Supri. We really looking forward to your offline talk at Planetarium soon. It will be wonderful for so many interested students to interact with you and ask questions. So we will be definitely having an offline session.
Thank you so much.
So thank you, Professor Supreet Singh, for that absolutely fascinating and illuminating talk on mapping the heavens, shaping the mind. Your presentation beautifully highlighted how astronomy is not merely about observing the night sky, but a profound synthesis of physics, mathematics, and engineering, driven by human curiosity and imagination. We are especially inspired by your insights on how ancient efforts to understand celestial phenomena laid the groundwork for modern science, and how the current technologies and missions continue to push the boundaries of our cosmic understanding. Your perspectives on India's role in global astronomy, from advanced observatories to remarkable space missions like Chandrayaan and Aditya L1, have provided all of us with a deeper appreciation for the vibrant scientific landscape we are part of. Our heartful thanks to Professor Singh for sharing his expertise, and the passion, and to all our participants for joining us today. We hope this session sparks curiosity and encourages many of you to explore further the wonders of the universe. Wishing you all a great day ahead and keep looking up. Thank you so much.
Thank you so much. Thanks so much.